Hi everyone. Today I'm going to solve a lead code hard problem. Problem ID is 1439 and the title says find the kth smallest sum of matrix with sorted rows. The title itself is not very intuitive, but let's see what this problem is, right? So you are given a matrix. You are given a matrix m by n matrix that has its rows sorted in non-decreasing order, right? And what it says is you are allowed to choose exactly one item from each row, right? So as to say, like if you have m by n matrix, there are m rows, so pick one item from each row. So altogether you have like total of n items, picking one entry from each row. So you form a vector of n items. Actually you form a vector of m items, total number of rows. And if you sum it up, right, if you sum it up, and what we are trying to do is, for all the possible vector combinations, what you can make out of this matrix, you have to find that vector with the least sum, right? And in this case, with that vector that has like kth smallest sum. So let's see further what this problem is all about. The reason I'm trying to solve this problem for you is there is no official lead code editorial solution for this, right? If you are struggling or if you are finding it difficult to solve this specific problem, I hope my solution is going to help you out. So let's see how you can go about solving this. I want to take the same example that's given in the problem section on the left of your screen and try to do a deep dive and write a code afterwards, right? So take this example. Take the matrix, the example one matrix that has two rows. The first rows with the sorted items 1, 3, and 11, and second rows with the entries 2, 4, and 6, right? So how can we take this example to understand the problem better? So let's try to do the same what the question has asked. There are two rows in this matrix. Let's try to construct the vector, what I discussed earlier, picking every single column items from every single row, right? So the row is indexed from 0 to 1 and the column is indexed from 0 to 2. So it's a 3 by 2 by 3 matrix, right? So from the first row you pick the first column, and from the second row you pick the first column. It's a 0 based index, right? 0 0. Similarly, from the first row pick 0, from second row pick 1, second column. And again from the first row pick the first item, from the second row pick the third item, or the item in the third column, right? So that completes a combination picking first item from the first row. You can do similarly picking second item from the first row and pick all three items from the second row, right? You see where it is going now. With that combination, I have listed out the value pointed out by those particular index. In the first case, it's matrix 0 0, sum up to matrix 1 0, right? That's like 1 and 2, which sum up to 3. If you see the last entry, right, pick the third item from the first row and pick the third item from the first row, that sums up to 17. So precisely the first and the last entry in this list of vector, what I listed, that's like the smallest and the largest. But in between, you cannot guarantee that these sums are in sorted order, right? So the reason why the first one is smallest and the last one is largest is because the rows in this matrix are itself sorted, right? So if you pick all the smallest item from all the rows, that's going to give you a vector with the smallest sum. If you create a vector with largest value from all the rows, it's going to give you the largest uh, vector with the highest sum, right? So there are possible, how many possible vector combination, how many possible vector that you can list out from the given matrix. That's a basic uh, problem with the counting, right? See, you can pick three different items from the first row and you can pick three different items from the second row, right? So from the first row, you can pick three. Now it's a basic principle of counting. And from second row, you can again pick three, right? If there was Third row, you could have picked three more items, right? So the total possible number of vectors, uh, what you can list out is, if R is the total number of rows and C is the total number of column in this matrix, that's like power of R. Uh, that's like power of C to R, right? Because total number of items that you can pick from the first row is total number of columns itself, right? And so columns times columns times columns, that goes up until as much rows as you have there, right? So it's typically listing out all these vectors is going to take you like r to the c, or in this case 3 to the power 2, 3 to the power 2, which is 9, right? So in this case we have like it's like power of 3 2, which is 9. So a very basic approach to solve this problem is to enumerate this list of vector and then sort it, and then from the sorted enumerated list of this vector you just pick the kth vector that's going to be uh, the desired result for you, right? Pick the kth vector and then have it sum. So how much time it's going to take? If you see, if the total number of vectors enumerated based on this principle is n, which is basically c raised to the power r. This is the notation I am following. Then sorting takes log of n log of n times, right? N log of n times, but you are not sorting a primitive type like int or character or double or float. You are basically sorting a vector itself based on the weight that you compute, right? Iterating through the matrix and getting the value and summing it up. So there are like a total number of column entries in this, total number of rows entries in this vector, right? Like if there are r rows, our vector length is going to be r, and then like you get the appropriate value or associated value from your matrix, and then sum it up. So that you are iterating r times here, right? So the constant involved here is on each operations you are doing it for like r time to sum up the value. So this is going to take like this much of time if you replace n with its appropriate value. N r times c to the power r log of c to the power r, right? So that's pretty much an exponential time. So how can we do it better here, right? Uh, so if you see, if you try to see this problem as a state machine, right? So obviously, when I list this out, the very initial state 0 0 with all the entries at 0 is like the seed state, which has the smallest value, because all the rows are sorted, so we are picking up smallest item from every single row, right? So if we begin from there, what can be its adjacent states that you can explore? Can we build some convention here, right? And if you see from a given state, right, from 0 0, that's like picking the first column from the first row and picking the first column from the second row, right? So let's say you want to alter this column value in each row, right? So two possible things what you can do is you go one column right on one row, or you go one column right on the other row, right? From 0 0 you can either go to 1 0 or 0 1, right? These are the potential next smaller values that this vector can yield, right? From the smallest one, uh, whatever its nearest state, those can yield you like the next smaller value. So those are like potential candidates for you to give next smaller value, right? So now that you might start seeing a pattern here. So since that we explored this state, what's the next potential smaller value as compared to this state? Those can be, again, you go for each index in each row, like for this vector, every single value is an index for that particular row position. You go one to the right, or for the other position, you go one to the right. From 1 0, you can either add one to the first value, go to the position 2 0, or you go keep the first column index as it is, and go one column right in the next row, right? And you see like this pattern goes on and on and on, right? But as you are exploring this, you see like lots of states what we explored seems to be repeated. There are so like 2 2 has repeated multiple times, 2 1 has been repeated here. uh, you see 0 2 is here. I see 0 2 somewhere else. No, not 0 2, but again 1 2 is here. You can see 1 2 here too, right? So now if you see this, if we start doing like a search from a very initial state, we might encounter states that are already explored, which we don't want to cache or keep in memory to do further search here, right? So how can you solve this problem? If you stop here for a little bit and think it loud. So you want to explore, and while you explore, you want to keep track of the smallest item, all right, for the next possible state you are exploring. And also you don't want the repeated items or repeated states. So two data structure, what should come to your mind is a priority queue. You want to keep track of the state so that your smallest state is always on top of it, right? That's one thing. The next thing is you want to keep track of all the states that has already been explored, so that you are searching in the set of list of states that has smaller population, right? You don't want repeated items, you don't want resistance. So the other data structure that will help you keep track of the explored state is set. So keeping that in mind, let's proceed with the solution. So, as I am talking about state, we need some abstraction to solve this problem here. So, first of all, I'm going to have a class called state. And I'm assuming, I'm not assuming, actually, I'm trying to force some property into this state. Uh, One is basically the sum or the weight, right? And next is what I want to do here is I want to get its children states. So I want to have a function uh, like a children here, right? So these two things, let's come back to this method later, right? Let's come back to this method later, but and also we need a constructor here. And what we pass in the constructor, let's come back to it later, right? So, but three things what we really need here is the sum to compare the state, and for every explored state, we want to get its adjacent states that are its immediate children, right? I'm trying to depict this whole problem as a graph problem here. So with that, what we can do is, uh, I want to, as I said earlier, I want to have a priority queue of this state. And I want to have a set of this state to keep track of things that are already visited and explored. Right. The next thing what I need is an initial state, right? So For now, I'm putting this as a null, and I'll come back to this later. And what I'm going to do is I'm going to push this initial state in our queue to begin our search. And we'll also mark this as visited to keep track of it. Right. What we'll do next is until we find the kth vector until we find the vector with the kth minimum sum, so we can keep decrementing k inside this loop. But what we'll do here is in each iteration, we'll pull a state with the smallest sum, right? We'll pull the state with the smallest sum, and what we'll do is for 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 this state, explore its children, and if this children is not visited, right? If this child is not visited, what do we want to do here? If this child is not visited, make sure you visit it. And also make sure you add that in your queue, marking it as the potential next smaller candidate, what you just currently visited, which is state. Right? So if you do this, then at the end of this loop, what's going to happen? You can just return state.sum because we are iterating only k times, and on each items that we are removing from this queue is a guaranteed next smaller item, right? So the kth items that you pop out from this queue is going to be the kth smallest sum of a matrix with sorted rows, as the question says. So you can return. So this is the high level algorithm here. Now how to make this code complete? One thing what needs to be done here is we need to initialize the initial state, right? There's something more to be done in this priority queue. We want to make it a min priority queue so that the smallest item always comes on top of it, right? So how do we do that? We need to make sure our comparator compares the sum. So let's have a comparator of state. Let's have comparator defined as taking two comparators. Comparator 1 and comparator 2, and it's comparing based on the sum. So if one is smaller, it's returning negative value. So negative value pretty much indicate that comparator 1 is smaller. If 1 is bigger, it's returning the positive value, which indicates that 2 is bigger, which indicates that 1 is bigger now. And if they are equal, it returns 0 value, right? So this is comparing based on sum to sort these vectors in an ascending order based on sum of this vector. So this would complete our priority queue. Now, how do we define the state, right? So in order to define the state, we haven't completed our constructor in our state class, right? So this state needs to maintain that vector of column index in each row, right? And somehow, like, we also need to have a sum value computed. So this state class needs to have access to our initial given matrix, right? That's one thing what it needs. And is there anything else what's needed here? Okay. And this also needs the initial vector. So let's have initial vector here, right? So we can have these things also as member variable here, matrix, and then list of integer as part of this class, right? So we can assign these things corresponding to these members. Now, how do we get the sum here, right? So first, in order to compute sum, what we need to do is for the size of the vector is total number of rows in the matrix, right? So I is basically like iterating through the rows, what you can assume here, right? So now we can update the sum as matrix. What's the row here? Row is I itself. And what's the column here? The column is the vector value in that particular position. So I value or ith position in that vector is representing ith rows, and the value is representing whatever the column that this vector is referring to, right? So you can pretty much get the value by index here. You can pause the video and think a little bit, you'll get convinced. So this gives us the sum. Now, how do we complete our children method, right? So for children, what we need to do is we need to return a list of adjacent states. So let's initialize an empty list of state. Let's call it child state new array list. And what we need to do is we need to create a state, all possible state, right? So for from a particular row, the current column index, what it has, should not cross the column boundary, right? So the value C, what's the column value that this particular row is holding is so if it is not the last column, if C is less than pick some rows and get its column. So this indicates that this is not the last column, so you can explore further, right? If this is not the case, then what you can do is we need to replicate the current vector and update it. So what you can do is child vector is new array list. So we can add the current state in this child vector, but we just need to update one particular index. This is not add, actually it has to be add all. So you are just cloning it, and you need to update one particular index, that is for this row. For this row, the column is C, so you need to make sure it is C plus 1 here, right? You're just moving one column right of what you have in this row currently. Now that you have a new vector defined, so you can create a new state and add in child state. Child states dot add new state matrix, and then this child vector. Okay. Now this is not complaining, so we should not be returning null, but we should be returning child states here. Okay. So this seems to be what it is. We have defined, or we have defined the states. Now what we have not done is we have not defined an initialized state, right, properly. The seed state, what should be initially pushed in our queue. So for that, what we need to do is we need to define a new state. List of integer. We need to create a vector. Basically, we need to create this vector, the root of this tree, right? If you, I mean, line number 26, that is highlighted. So for each row, we want to pick the first column, the 0th column. So list of initial vector is new array list. So for all the rows, we need to add 0th column for all the rows. Now this will define the, we can define the state, pass the matrix, and then pass this initial vector. So this will define the state, initial state, right? Q dot add is okay. Now Q can be resolved, so it's not complete. So this seems like this is a complete thing. Now if you run it, let's see we get the right answer. So this is giving me 9, but expected answer is 17, right? So what's the problem here? If you, let's just read through the code, right? So we have a comparator to compare the state based on its sum, and then we have a priority queue, a min heap based on the vector sum, right? So we already defined the constructor here, so that's why passing this comparator to our queue is making this a min heap of our vector. Now we have a set of states to keep track of thing, and then we have an initial state where we are picking all the 0th column from all the rows. We just define a list with all entries at 0 of size matrix dot length, and then we have added that in the queue. We have key map that is visited and define an initial state based on that, right? So now we are iterating for k times, and on each iteration we are decrementing k, right? Assuming that the kth item that's popped out from our priority queue is like the kth smallest vector with sum of items that this is pointing in the given matrix. So we pop out the items from the queue and then explore all its children. If any of those children are not visited, we make sure we visit and add them as the potential next smaller candidate here. Now, then it seems like it is right here. Let's go and see if we did correct thing with the sum here. We could use the debugger, but let's just walk the code verbally here, right? We have properly reference matrix and vector, whatever that's passed. But let's see if we have computed the sum correctly or not, right? For all the items in the vector, we have sum. I is going to be the row, and whatever the value in that row, in that position for that vector is going to be the column index for that row. So that has to be sum. For children, we are iterating everything. We are getting the column value for this particular row. And if column is not something, the last column for this particular row, the last column would be like matrix length minus 1. So it has to be smaller than that. So we are checking the rightmost bound here for the column, and then creating a new list, adding the entire current state in this new empty list as the child vector. But what needs to be changed is for this particular row, we want to move column 1 to the right. So whatever the current column is, we are adding 1 and setting it there. And then we are creating a new state based on this child vector and adding in our list of child states, which will eventually return. So if you are a Java developer, or if you are used to any other programming language, one thing what is missing here is, so we are using a hash set here, right? This hash set is not based on any primitive types. This hash set is based on composite type state. And the other thing is, uh, so that's one thing, right? So what needs to be done here is we need to have some kind of uh, method that supports us to put this composite type in our hashed data structure. What needs to be done here is we need to complete two methods. That's basically equals and hash code. Hash code has to be unique based on our vector, right? So vector is obviously a list. Assuming that the hash code for the list is well defined, uh, given by the library, we can just make use of that here. And the next thing is, since that we are using the state class in hash set itself, we need to override equals method with the custom equals logic. So this state is unique based on the vector itself, right? Sum is like computed once we already have the vector, but if vector is unique, the sum is going to be unique. Not necessarily sum is going to be unique, but vector is going to, this state is going to be unique based on the uniqueness of the vector, right? So, sorry, not hash code, I wanted to write equals. So equals takes so some object. So what we want to do here is typecast that object. And return if the current vector is equal to the vector that's provided in this equals method. So whatever the vector, that the object we are comparing, so we are simply doing equals on that particular vector for if those two lists are same amount, right? So if we add these two method, I assume this has to be run until there are other bugs in our code. So this is accepted, and if I submit it, let's see how it's going to work. Okay, this is accepted. So my solution is 56%. It beats 56% of the solutions that Java user has, and the memory consumption seems to be 17% of all Java users. That's not too bad. All right. So what did we do here? If we did not enumerate everything, is we are partially filling our data structure here. So we are partially filling the data structure and not enumerating entire vectors. So that's saving us in memory as well as the time complexity, which was going to be exponential earlier. I hope you like my solution. Uh, Please like, subscribe, leave some comment, and if you have more questions, you can always email me. You have a very good rest of the day, and as my channel logo says, always live, laugh, and love. Thank you.